All right, in this video, we're going to continue finding Laplace transforms. In particular, we're going to look at functions where there is an exponential term in the numerator. The main property that we're going to use to evaluate these is this one. It says the inverse Laplace transform of e to the minus as times f of s is equal to the Heaviside function of t minus a times f of t minus a. So notice here the inverse Laplace transform of f on its own is just f of t. So but once it's in this combination, then we shift the origin. Okay, so our approach will be, for each case we're going to write the function in this form. Then we're just going to work on the inverse Laplace transform of f. Once we've got it, then we plug into this formula. So let's start with the first one. So in A we have so the function g is se to the minus 2 s all over s squared minus s minus 2. So if we write this in the form e to the minus 2s f of s, this implies that f of s is s over s squared minus s minus 2. So if we can find the inverse Laplace transform of this, then we have the inverse Laplace transform of that naturally. So the first thing we're going to do with this one is to factorize the denominator. Denominator is going to factorize to s minus 2 into s plus 1. Then this we can write in terms of partial fractions. So we decompose it into partial fractions. Then if we multiply everything by this denominator here, then the left hand side is just going to be s, the right hand side is going to be a into s plus 1, b into s minus 2. The two roots of this denominator are 2 and negative 1. So we use those to find these unknowns. So if you plug in s equals to 2, this left hand side is going to be 2. The first term on the right hand side is going to be 3a. The second term is going to vanish. So this is telling us that a is 2/3. Then if we plug in s is negative 1, the left hand side is going to be negative 1. The first term is going to vanish. This one is going to be negative 3b. So from this, b is equal to 1/3. So what it means is that the function f we can write as follows. So f we can write as 2/3 over s minus 2 plus 1/3 s plus 1. Then we can find the inverse Laplace of f. So the inverse Laplace of f is going to be 2/3 the inverse Laplace of 1 over s minus 2 plus 1/3 inverse Laplace of 1 over s plus 1. The first one is e to the 2t, and the second one is e to the minus t. So this is f of t. So according to that theorem, therefore the inverse Laplace transform of e to the minus 2s f of s is equal to h of t minus 2 f of t minus 2. So all that we need to do is to plug in t minus 2 for every t here. So what that is going to give us, if we just factor out the 1/3, because both terms have got 1/3 there, then h of t minus 2, then we're going to have 2e to the power 2t minus 2 plus e to the power negative t minus 2, which is going to be 2 minus t. So that is going to be the inverse Laplace transform of the function we started with. Okay, so now going to part B. So in part B we have got e to the minus pi s all over s cubed plus s. So this time writing this as e to the minus pi s times f of s implies that f of s is 1 over s cubed plus s. If we factorize the denominator, it's going to be s squared plus 1. Squared plus 1 is an irreducible quadratic, so our partial fractions will look something like this: s squared plus 1. If we multiply through by the denominator, then we're going to have 1 is equal to a into s squared plus 1 bs plus c times s. If we multiply out here, we're going to have a s squared plus a bs squared plus cs. Now the terms involving s squared are going to be these two. So times s squared here. The only term involving s is this one, and the only constant is this one. So if we start by matching powers of s to the power 0, on the right hand side we've got a, on the left hand side we've got 1, and then powers of s to the power, or coefficients of s to the power 1. On the left hand side we've got c, right hand side, and then this side there is no term involving s, so that means c is 0. Then finally coefficient of s squared on the right hand side is a plus b. Here on the left hand side there is no s squared, so this is equal to 0. So that means a and b are going to have opposite signs. Since we've already found a to be 1, b is going to be negative 1. From this, our function f can be written as follows. So a is 1, b is negative 1. Okay, then the inverse Laplace of f going to be the inverse Laplace of 1 over s minus the inverse Laplace of s over s squared plus 1. Inverse Laplace of 1 over s is 1. Inverse Laplace of s over s squared plus 1, if you just check the table, okay, so yeah, if we check the table here, the inverse Laplace of s over s squared plus 1 is just going to be cosine t. So that means this is just going to be cosine t. Again, this is f of t. Therefore, the inverse Laplace of e to the minus pi s all over s cubed plus s is going to be the Heaviside function of t minus pi times f of t minus pi, where f of t is that. So it's going to be 1 minus cosine t minus pi. Okay. Then cosine t minus pi is going to be cosine t cosine pi plus sine t sine pi. Cosine pi is -1, sine pi is 0, so this term is going to be 0. This first term is going to be negative cosine, so that means our inverse Laplace transform, which is going to be g of t, will be h of t minus pi into 1 plus cosine t. So we can write it like that. Okay, so that is part C. We still have that is part B. Okay, so what we are going to do now is part C. So in part C we have got g of s, which is s plus 1 e to the minus pi s over 2, all divided by s squared minus 4s plus 5. So if we write this as e to the minus pi s over 2 f of s, then f of s is going to be s plus 1 divided by s squared minus 4s plus 5. But then you're going to find that the denominator here is not factorable. So what we're going to need to do is to complete the square. If we complete the square, this we can write as s minus 2 all squared plus 1. Once we've got s minus 2 here, we need s minus 2 in the numerator as well. So we're going to manipulate the numerator algebraically. So we're going to write this as s minus 2 plus 2 plus 1, and let me do it like this. So what we're going to do is we're going to write this as s minus 2 plus 2. So the minus 2 plus 2 is our algebraic manipulation. Of course, minus 2 plus 2 cancels out. But then what we're going to do is we're going to write this as s minus 2, then plus 3. And then we're going to write this as two fractions. So s minus 2 over s minus 2 all squared goes on its own, and then 3 over s minus 2 squared plus 1 goes on its own. Then the inverse Laplace transform of this, so this one from the table, got s minus 2 over s minus 2 squared plus 1. So from the table, it's this one here. A is 2, B is 1. So this is going to be e to the 2t cosine t. And then the other one is going to be 3e to the 2t sine t. Okay. So from that, the inverse Laplace transform of e to the minus pi s over 2 times f of s okay, so this is going to be h of t minus pi on 2 e to the 2t minus pi on 2. That's going to be for both of these two terms. And then we're going to multiply by cosine t minus pi on 2 plus 3 sine t minus pi on 2. And then we can simplify this using trigonometric identities. So we're going to get e to the 2t minus pi h of t minus pi on 2 then times, it's going to be sine t, the first term, and the second term is going to be minus 3 cosine t. Okay, at this point we're going to give you the opportunity to have a go at the last two examples here. So if you'd like to have a go at D and E, you can pause the video, work through them, and then when you continue the video, you can compare with our solutions. All right, so we're now going to scroll down to our solutions for D and E. By the way, if you have got any questions or comments on what we do, you can post them in the comment section. Similarly, if you find these useful, you can let us know. That's going to encourage us. And of course, please do subscribe to our channel. That's going to go a long way as well. So for D, if we write this in the form e to the minus s times f, then f is going to be this function here. The denominator factorizes as follows. So that means we can set up our partial fractions like that. If we clear the fractions, this is the situation we're going to have. We have got two roots here. When we plug in the first one, which is 0, get b is 1/2. When we plug in -2, get c is -1/4. Then if we just plug in 1, b and c we already know, so we can plug them in here. Then we find that a is 1/4. So for our function, we can write it like this. When we do the inverse Laplace, this one will be 1/4. This one will be t on 2. This one is going to be 1/4 e to the minus 2t. So this is our f of t. Then for this one, we're going to have to plug in t minus 1 there. So when we do that, this is what we get. For e, so our f is going to be this function here. This can be further factorized. So we're going to have 3 partial fractions. we clear the fractions, we're going to have 3 roots this time. So plugging 0 gives us a is 5/3. Plugging 1 is going to give us c is -1. Plugging -3 gives us b is -2/3. So our function we can write like this. Its inverse Laplace transform is given by this function. Then the inverse Laplace transform of the original function is going to be the Heaviside function of t minus 4. And then every t here is going to be replaced by t minus 4. Thank you.